All right. Welcome everyone to our TCS Plus talk on today. Our speaker is going to be Thomas Steinke, who is at Google DeepMind, and he's going to be talking about his work. As you can see, titled the like a discrete Gaussian for like a differential privacy. And this work is especially exciting because it recently won the Casper Boden Award for outstanding research in privacy enhancing technologies. And this is an award given out for sort of like an impact of this work. As we'll see, this was a big, important, and impactful paper. So it's like welcome, Thomas.
Thanks for the introduction and thanks for inviting me. So I'll get started by giving you a brief history of this problem and this work, and it's also going to serve as an outline for the talk. So back in 2006, we get the beginning of differential privacy. And one of the key methods here is to add Laplace or Gaussian noise to a sensitive value in order to protect private information that value was computed on. And the idea is basically that you'll get sort of similar output distributions. I'll go into that in a bit more detail shortly. But it's worth noting these are real value distributions. And when you implement this on a computer, you're going to use floating point numbers. And in 2012, a paper by Ilya Mironov showed that using floating point implementations of these distributions is actually insecure. There's like a catastrophic privacy failure. And the high-level idea is that if you look at the low-order bits of the output, this isn't correctly distributed, and you can basically reveal the private information due to numerical errors. So that sort of leaves us in an awkward position. We have this nice theory, but implementing it doesn't quite work. So the obvious thing to try doing is rounding. And that kind of works, but it's messy. And then the next question is, well, what about a discrete distribution? Instead of having a distribution that's on the real values, can we come up with something that's supported on the integers? And there's one previous work which came up with a discrete version of the plus mechanism. But there's a couple of issues here. First off is like, how do we actually sample from this distribution in practice? And is there an analog for the Gaussian? And that's basically the starting point for this work. But we didn't really have a great idea until we had a serendipitous tweet. So this tweet came out March 10th, 2020 by my co-author Gautam. And I saw this and I thought, hey, this seems kind of relevant to the kind of sampling of discrete distributions for differential privacy. So me, Gautam, and Timon started talking. And 3 weeks later, we had a paper on arXiv. And I have to say, this is one of the fastest papers I've ever written. Obviously, the first version was kind of short, and we had to do a bit more work to beef it up. But that's kind of how we ended up with this paper. It's just a serendipitous collaboration. And the message of the paper is pretty simple. So first, we show that discrete distributions are equally good in terms of privacy and utility as continuous distributions, and in a sense, they're actually better. And we also gave efficient algorithms for sampling from these distributions. That's gonna be the meat of this talk. I'll tell you about how those algorithms work. So after we put this paper out, it ended up getting used in a high impact use case, which is for ensuring privacy of data released from the 2020 US Census. So the output of this algorithm ended up affecting things like congressional redistricting. And then earlier this year, we won an award for this work, and that's what led us to having this talk here. Okay, so that's the brief overview, and now I'm going to basically go through that in more detail. All right, so let's start with the definition of differential privacy. I don't know if you've seen this before, but the basic idea is we want to ensure that an algorithm doesn't release information that's highly specific to one individual. And the way we formalize this is by saying that if you change the data of one individual, so you've got two input data sets, X and X prime, that differ only by one individual's data. So one individual was added or removed or replaced. And then the output distributions should be similar. Now, there's different ways of quantifying similarity of distributions. The standard one is epsilon delta dp. We assume that the probability of an output has a multiplicative e to the epsilon factor plus a delta additive factor. And then there is a different definition called concentrated differential privacy, where we measure similarity in terms of ringy divergences. Now, this is a little bit better motivated from the information theory side. I'll flash up the definition of ringy divergence, but I don't really expect you to digest this if you haven't seen this before. So that's the definition of differential privacy, and that is basically the goal for designing algorithms. Okay, so now one of the key methods for ensuring differential privacy is adding Gaussian or Laplace noise to a query that has low sensitivity. So a simple example would be we have some count inquiry. How many people in the data set are attending a certain conference? How many people are, have a certain disease? These are sort of integer value queries. The sensitivity is 1 because you can only add a single person's data can only change the outcome by 1. And then we add Laplace or Gaussian noise. And then you'll get a plot like this in terms of the output distribution. So if you change one person, you're going to shift the distribution, but the distribution has enough variance that it's actually hard to distinguish the two outputs. So they give you one sample from either of these distributions, you're not going to be 100% sure which one it is. Now, these are obviously continuous distributions. They're supported on all of the real numbers, and that means that we just cannot sample them on a finite computer. So there's like an obvious disconnect here between the theory and the practice. And as I mentioned, the obvious thing to do is just use floating point approximations to real numbers. But there was a paper by Ilya Mironov, 2012, that showed that this actually doesn't preserve privacy. And again, the issue is that the low order bits are compromising the privacy. But people were still using this because there just aren't a lot of alternatives. And I think it's important to emphasize that this is a big problem in the sense that the privacy violation that you get essentially reveals noiseless answers. So you've basically added noise, which has a cost in terms of utility, but you're not actually getting privacy if an adversary is looking at the low order bits of your app. Okay, so let me give you a little bit more detail about the attack that Ilya Mironov presented. So here's the standard method for generating a sample from a Laplace distribution. So you generate a random sign, S, and then you take a uniform random variable, U, and you multiply the sign by the log of the uniform random variable. And that's going to give you a Laplace distribution. And there's two problems that come up here. So first off, in the floating point world, U is going to be a floating point number. And generating a uniform floating point number is kind of problematic, especially when you get close to 0. But the bigger issue is that applying the logarithm is going to distort the low order bits of the distribution. And here is a figure from the paper that kind of shows you what the issue is. So you start out with uniformly spaced floating point numbers. That's what you're sampling from U. You take the natural log, and then it's going to sort of bunch them up. So there's going to be different floating point inputs that map to the same output of the log. And you also get the other problem if you look elsewhere on the input space, where rather than outputs bunching up, they end up being separated. So you end up getting output values of floating point numbers that are not realizable. So basically, there's holes in the support of the distribution. And if you shift the distribution, which is what you're doing when you add it to a low sensitivity query, those holes are not going to align. And you're going to be able to tell by looking at the value. You'll say, well, look, this value would have a hole under distribution mx, but it is in the support of mx prime, so I know that the input was x prime. And that's the basis of the attack. And what's really perverse is that if you make epsilon smaller, this should make privacy better, but it actually makes the attack more effective. And what was demonstrated is if you set epsilon to be 10 to the minus 6, which is basically great privacy, then you can still perform a complete reconstruction attack of the input data. Now, the obvious solution to this is to do some kind of rounding to kind of hide those low order bits. This is messy for a couple of reasons. And I'll also show you later on that this doesn't work quite as well as the discrete distribution. Anyway, this is the background for our work. We see there's a problem with floating point numbers, and the obvious question is, why don't we just use a distribution that is inherently discrete and avoid all the issues of floating point numbers? Okay, so that's precisely what we propose. So we propose a distribution that is a discretization of the Gaussian. Now, it's worth noting that this distribution is not novel. People have studied this before. In particular, it gets used in lattice-based cryptography, but we're using it here for a new application of privacy. So obviously, this is a discrete distribution. It's only supported on the integers. And basically, the probability mass function is just a rescaling of the probability density function of the continuous Gaussian. There is prior work that does a discrete Laplace distribution. And as I'll mention later, the discrete Laplace, just like the continuous Laplace, has higher variance than the discrete or continuous Gaussian. Right, so the key contributions from our work are that we did a privacy and utility analysis of the discrete Gaussian distribution, and we also gave an efficient sampling algorithm, not just for the discrete Gaussian, but also for the discrete Laplace. Okay, so let's just start by doing a comparison in terms of privacy and utility between the discrete Gaussian and the continuous Gaussian. Again, here's the definition of the discrete Gaussian. And our results show that you have essentially the same privacy guarantee. To be specific, if you add noise to a sensitivity 1 query, then you're going to get concentrated DP with parameter 1/2 sigma squared. This is for discrete Gaussian, and it's also the same guarantee you'd get for continuous Gaussian. In terms of approximate epsilon delta dB guarantees, they are very similar, but not quite the same, and I'll show you a plot to illustrate that. So here is a plot of the epsilon delta guarantees that would get from adding discrete and continuous Gaussian noise, where the sigma squared is 100, to a sensitivity 1 query. Now, you can see there's a solid blue line and a dotted red line, and they're just indistinguishable. Those are the guarantees of discrete and continuous Gaussians. They're completely indistinguishable. There is a third line, which is the third yellow line, which is an upper bound that's implied by concentrated DP. Okay, so this is for sigma being 10. What happens if we make the sigma smaller? Well, then we can start seeing that there is a difference between the privacy guarantees of the discrete and continuous Gaussian. In particular, the discrete Gaussian ends up having kind of a bumpy trade-off curve between epsilon and delta. So they're not exactly the same, but for the parameter regimes of interest, they are basically indistinguishable. This is actually a very low level of noise, so poor privacy if we're doing this. So this plot is just sort of showing the limits. It's not the parameter regime of practical interest. Okay, so that was the comparison in terms of privacy. Now the next thing I want to talk about is how it compares in terms of utility. So in terms of variance, they're essentially the same. However, the variance of the discrete Gaussian is slightly smaller than is always smaller than the continuous Gaussian. For large sigma, which is the parameter regime of interest, they're very similar. But for small sigma, they diverge. So here's a plot to illustrate this. So on the x-axis, I'm changing sigma. On the y-axis, the sigma parameter on the y-axis, I'm showing you the actual variance. So the continuous Gaussian, which is the dotted red line, is just a y equals x relationship. We know that sigma squared is precisely the variance. The discrete Gaussian, which is the solid blue line, as you can see, it's below the continuous Gaussian. So the variance is smaller. It's close for large sigma, but as sigma goes to 0, there is a divergence. Now there's a third line on the plot, the dashed green line, and that's what happens if you take continuous Gaussian noise and do rounding, which is, again, an obvious alternative to doing an inherently discrete distribution. But what you see is this actually has higher variance than the discrete Gaussian. So in this sense, we're doing better than the rounded continuous distribution. So that's in terms of variance. We also looked at the tail behavior, the moment generating function. It's basically the same as the Gaussian distribution, the continuous Gaussian. Okay, so I've told you the comparison between discrete Gaussian and continuous Gaussian. The TLDR is that they are essentially the same. But the next question is, well, what about Gaussian versus Laplace? Now, this is something that's actually not specific to the discrete distribution. So everything I'm going to say on this slide applies equally well as the continuous distribution. And it's something that actually I think is an important lesson. So an obvious question is, why should we use Gaussian instead of Laplace? And there's a simple answer which says that if you stick to if you stick to concentrated DP, the Gaussian distribution will actually provide lower variance than the Laplace distribution. Now that's specific to concentrated DP. What about approximate DP, which is the standard definition? In this setting, if you have high levels of composition, there is actually a significant advantage to the Gaussian. So when you're doing composition, which basically means answering lots of queries, lots of independent queries, the Gaussian is advantageous. And I'm going to show you some plots that show this difference. So here, what I'm doing is I'm answering an increasing number of queries. So the x-axis is the number of queries I'm answering, ranging from 1 to 100. And I'm setting the noise variance so that the overall privacy is epsilon equals 1, delta equals 10 to the minus 6 dp. And what I'm plotting on the y-axis is the variance of each query, of the noise being added. And you can see that for small numbers of queries, specifically for less than 10 queries, Laplace is actually better. But for a large number of queries, there is a big gap, and Gaussian noise is preferable. And this is obviously very important in practice. I'll also show you a second plot with kind of the same message. So here I'm fixing the number of queries at 100. but I'm showing you what happens if you vary epsilon and delta. So I'm fixing the number of queries, I'm fixing the standard deviation of the answers, and I'm showing you what the privacy guarantee looks like. So as we trade off between epsilon and delta, so if we increase epsilon, the delta will decrease. And we see that for reasonable values of delta, the Gaussian gives you a better epsilon, unless your delta is like 10 to the minus 45. So the point of this slide is to say that the Gaussian mechanism is better than the Laplace mechanism in settings where you have high levels of composition. Composition meaning answering independent queries. Okay, so now I want to tell you about our algorithm for sampling a discrete Gaussian. Here it is on one slide. I don't expect you to parse this right now. I'm going to go through this step by step. But what you see on this slide is that it's not a complicated algorithm. It's something that fits on one slide. So again, it's a simple algorithm. It's efficient, and I'll be a little bit more precise about that, but roughly it's a constant time algorithm. And it's practical, and we put some code on GitHub if you want to try it. Okay, so let me get into how the algorithm works. So the basic idea is rejection sampling. So the idea of rejection sampling is, suppose I have a distribution that I can sample from. And for now, let's assume we can sample from a discrete Laplace distribution. And there's a distribution that I want to sample from, in this case, the discrete Gaussian. What I can do is I can sample from the discrete Laplace distribution and then decide whether or not to accept the sample. And if I don't accept the sample, I'll try again. And then I output a sample from this new distribution, from the discrete Gaussian. And it's kind of on this plot. So basically you get a sample from the blue distribution, which is higher. You want to get a sample from the orange distribution, which is lower. So you sample from the blue, and with probability, that is the ratio of the orange to the overall size blue, you accept it. I'm realizing this plot probably doesn't work very well if you without color.
Thomas, we have a question in the chat. Can the difference between a Laplace and Gaussian noise be formalized and generalized, for example, depending on the preakness or the higher order moments of the distribution?
That is a good question. It's a little hard to generalize given that we only have like n equals 2 examples. Like I do feel there is some sort of general principle at play here, but it's hard to really state something given that there's only 2 distributions that we're looking at.
Thanks.
Okay, so I'll be a little bit more precise about this. So let's assume for now that we have a mechanism for sampling x from a discrete Laplace distribution. So that means that x has a probability density that's proportional to e to the minus absolute value of x over t. So now what I'm going to do is I'm going to accept x with probability, with this probability, and you'll see how the math works out in a second. And if we don't accept, so if we reject, then we'll just try again, try and compute another sample and accept with that probability. And then if we look at the conditional probability, so the probability of an output x conditioned on accepting, then you'll see that there's a simple calculation. I don't expect you to work all this out, but basically you get a discrete Gaussian out of this because the absolute value and the acceptance probability cancel out, and you insert a minus x squared. So it's a very simple calculation. It says that if you do this rejection sampling, you'll get from one distribution to the other. So that is the outermost step of our algorithm. We start with a discrete Laplace, and then we do rejection sampling, we get a discrete Gaussian. That still leaves the obvious question, how do you sample a discrete Laplace? So there's two ways to do it. The simplest way is to see that a discrete Laplace is a geometric random variable with a random sign. You have to be a little bit careful because you're double counting 0, like plus 0 minus 1. So we also need to do a little bit of rejection sampling here. An alternate way to do this without rejection sampling is just to take two independent geometric random variables and take the difference. So that's how we sample a discrete Laplace, given that we can sample a geometric random variable. Obvious next question, how do we sample a geometric random variable? So now we've gotten rid, so the first reduction, we got rid of the squared to an absolute value. The second reduction, we got rid of the absolute value. So now we're just sampling e to the minus x as a probability mass function. So the simplest algorithm for sampling a geometric is just to keep flipping a coin until you see a heads. That's going to generate a geometric with parameter t equals 1. Oh, sorry, t equals 1 over log 2, to be precise. If you bias the coin, you're going to get the appropriate geometric distribution. However, this is quite slow when the scale is large. Like if you want to generate a geometric with scale 1,000, you're going to have to sample roughly 1,000 coins. So we have a method of accelerating this, and the idea is that we're going to generate the high order bits and the low order bits separately. So the high order bits is basically x over t rounded down floor. This we're just going to do with repeated coin flipping. Now this is basically a geometric with scale 1. And as a result, an expectation, we're going to need to sample a constant number of coins for this. Now the low order bits is x modulo t, and we're going to do this with our favorite tool, rejection sampling. So we're going to sample a uniform v between 0 and t minus 1, and we'll accept it with probability e to the minus v over t. So if independently generated u, the high order bits, and v, the low order bits, and we just add them back together. And that's our algorithm for generating a geometric random variable with constant time complexity, effectively. As I stated it, the algorithm works for integer t. It can be extended to non-integer t too. Okay, so I've now given you 3 different reductions, and that's what this algorithm is doing. Now, the parameter t is not super important. Any value will give you a correct algorithm. We have to choose a good value to make the algorithm efficient, though. But the thing that's maybe sticking out here is that I need to be able to sample a Bernoulli with expectation e to the minus gamma for some parameter gamma. So I still need to come up with a routine for sampling from a Bernoulli with probability e to the minus gamma. So how do we do that? That's where Gautam's tweet comes in. So Gautam's tweet is precisely the algorithm that's missing to make our method work. So let me explain roughly how this works. The high-level idea is we're going to take the Taylor series for e to the minus x and turn it into an algorithm. So we're sampling a random variable k such that the probability k exceeds little k is x to the k over k factorial. So now the probability that this variable k is odd, do a simple bit of math, and you get precisely e to the minus x. So that is our algorithm. So we start with k equals 1. We sample a Bernoulli with parameter gamma over k. If the Bernoulli comes up 0, we stop with computer.value k. If the Bernoulli comes up heads, we increment k and continue. And that's going to generate a k with precisely this probability. The probability of exceeding the value k is gamma to the k over k factorial. And then we just decide whether or not it's odd. So that is the algorithm for sampling from a Bernoulli with e to the minus x as a parameter. And the key thing here is we're avoiding any kind of floating point computations. Because the obvious thing to do would be to compute e to the minus x, but that requires you to move into the floating point world. Now, it's worth noting that this definition only works for x being smaller than 1. And that's easy enough to fix just by repeating multiple times. Okay, so I've now described to you the whole algorithm. Let's talk briefly about the efficiency of the algorithm. So there's a certain closure here. So if I start with a parameter sigma squared that is rational, then all of the operations of my algorithm is going to be restricted to integer or rational values. So we don't have to use floating point numbers at all. And that is great. That means we don't have to worry about floating point errors causing us privacy problems. And if you look through it, there isn't any sense in which the complexity of the numbers blows up in a bad way. So there's no like hidden issues here. If you look at the algorithm, it's basically a couple of nested loops. So there's a fairly easy thing to do a runtime analysis on. Each of those loops runs a random number of times, but it's sub-exponential. So the overall runtime of the algorithm is sub-exponential. And the expected number of operations is constant, regardless of the parameter sigma. So there was some follow-up work that asked the question, okay, is the algorithm susceptible to timing attacks? If I know how long it took to sample the noise, does that tell me something about the value of the noise and thereby about the private information? So one way that we can reveal information is when you're sampling the high order bits of the geometric by repeated coin flipping, the runtime of the loop is directly proportional to the value of that thing. And the good news here is that because we have the sub-exponential runtime, we know that the algorithm is unlikely to take a long time. And we can then sort of use various tricks to ensure that we're not leaking information. So just to be precise about what I mean by sub-exponential runtime, suppose I want to generate k samples as a batch, then the amount of time it takes is going to be order k plus log 1 of a delta with probability at least 1 minus delta. Okay. So that's all I want to say about this paper. I wanted to briefly end the talk by talking about some of the subsequent work. And one of the subsequent pieces of work, which is also by myself, is on distributed noise generation. So one of the nice properties of a continuous Gaussian is that if you add multiple independent continuous Gaussians together, you get another continuous Gaussian. And this is useful if you're generating noise in a distributed fashion. And in this work, we showed that the discrete Gaussian also kind of has this property. Unfortunately, it's not perfect. So the sum of independent discrete Gaussians is not quite a discrete Gaussian, but it's extremely close to one. So there's this result. which shows that the max divergence, so the maximum ratio of probabilities, is quite small. So there's this expression. And just to give you an idea of how good this result is, if the variance proximity of the Gaussians is at value 3, which is quite a small value, then the max divergence between the sum and a single continuous discrete Gaussian is less than 10 to the minus 12, which is extremely small. And if you make the variance proxy larger, it's only going to get a better bound. So that's a very nice property of the discrete Gaussian. Now, the most high-profile use of this mechanism was for the 2020 US Census. So I just want to have a very brief slide on that, with the disclaimer that I don't actually know too much detail about what the census did, since I was not directly involved with that. The high-level story is that what the census was doing was just answering a huge number of count inquiries. And I mean literally billions of count inquiries. And those count inquiries were very, they were all the following form. So for example, I might be asking how many people live in a certain geographic area, and have a certain gender and a certain age and a certain mix of race and ethnicity. And you're going to have like every possible combination of these parameters. And that's a count inquiry that you're going to ask. Now, here's a figure from one of the papers that the Census Bureau released showing how they did this. So these count inquiries are in a geographic hierarchy. So first they ask count inquiries at the national level, how many men aged under 18 or Black are there in the country. Then they ask those same queries at the state level. Then they do this at I think the total hierarchy is something like 8 levels. Then it'll be county level, census tract level, and then it'll come down to census blocks, which are basically like city blocks. And there's just a huge number of queries. And what they did is they answered each of these queries with an independent discrete Gaussian. Now, in terms of the privacy analysis, you have to be careful about the sensitivity. Each person can contribute to some subset of those queries. So, your data is used at each geographic level, at your block, at your county, at your state, at the nationwide level. And it's also, but there's also a sense in which it's disjoint, like you're only going to be counted in one block, you're not going to be counted in other blocks. So there's some care required in the analysis and in setting the parameters. But basically, once you do that, the remainder of the work is some post-processing of these outputs to ensure that the numbers are consistent. So obviously you want that the numbers summed over the states will be consistent with the national levels. And you also want to have negative values, because adding the noise could in principle produce a negative value. And that is the high-level overview of what they did. And this data was used for many things, including redistricting for the US Congress. Okay, so now we can wrap up. I just want to summarize again. So the motivation for the work is to avoid the difficulties with floating point implementations, because there's a disconnect between the theory of differential privacy and the practice, which, continuous versus discrete. And we show that the privacy and utility guarantees between the continuous and discrete Gaussians are essentially identical. And our other contribution is a efficient sampling algorithm. So that is the talk. Thank you very much.
Thank you, Thomas. So now we like I'm taking any questions. So in the audience, you can either like unmute yourself and ask, or you can like type things in the chat, and then I can like ask on your behalf. Yes, Ahmed raised a hand.
Yeah, thank you for the great talk. I just wanted to ask, I don't know much about differential privacy, but does the performance, like you compare the Laplace and the Gaussian, does it also depend on the underlying distribution of the variable you are adding noise to?
So I think what you're getting at is that there may be different utility functions in terms of like how sensitive we are to the noise. And yeah, obviously there's different utility functions that would give you a different preference. In terms of my comparison, I showed the variance, which I think is a reasonable proxy for like what you care about. Another thing you could look at is kind of some kind of tail bound, like what's the width of a 95% confidence interval? The Gaussian has a lighter tail, so that would actually be a more advantageous comparison for the discrete Gaussian. But there are other utility functions that you might be interested in that are sort of much more sensitive to what's the probability of being very close. And in that case, it is possible that the Laplace is actually better. But if you ask the question with too much generality, you're not gonna get an answer. I think looking at the variance is a reasonable answer.
Thank you, but I don't know, maybe I wasn't very clear. Like I also, so that was my first question. Thank you for answering. And then I was also wondering if, so you're adding noise to a variable, right? And does the distribution of the variable before the noise matter? So if the distribution is Gaussian or something else, does it matter?
Yeah, so I mean, usually in the differential privacy literature, we're doing like frequentist statistics, so we don't talk about the distribution. But you're absolutely right that it could matter, and I do think that in terms of the downstream use cases, for example, the census, they are happier with Gaussian because that's often the kind of assumption they make for the underlying data, and then you're adding a Gaussian, kind of, it makes the analysis easier than having some other distribution. Obviously, it could be different. Maybe you have a different assumption on the underlying distribution.
Thank you.
We also have a question in the chat. Mike asks whether moment accountant type analysis work also for the like a discrete Gaussian in the same way they work for the continuous Gaussian.
Yes. So we focused on concentrated differential privacy. The moments accountant / Renyi differential privacy is more general than that. But for the Gaussian, there's not really a difference because the Gaussian has a very nice has nice moments, nice Renyi DP guarantees that correspond exactly to concentrated DP. So the answer is yes, but it's like it doesn't change the story relative to concentrated DP. I guess the obvious follow-up question is what about these like Fourier-based accountants that are doing exact accounting? That's actually kind of an open question. However, there was a paper by Weijiasu and some co-authors that went on arXiv like a week ago looking at this question.
Cool. Okay, we have another question in the chat. Peihan asks that he noticed that the use of the PSRN, partially sampled random number, in privacy computation libraries such as OpenDP for numerical sampling from continuous distributions, and he's curious what the main difference between the a PSRN plus a continuous Gaussian versus a discrete Gaussian. Can you explain how these approaches differ in practice?
I'm not familiar with the PSRN stuff, so it's hard for me to compare.
Okay.
Sorry.
Sure. Yeah. Okay. Then if there's no more questions, let's thank our speaker again, and we'll end the recording.